Donc merci d'être venu à ce jury. Je me présente, je suis Christian Tenot, je suis directeur de recherche au CNRS. Je vais vous présenter les membres du jury, en commençant par les rapporteurs. Donc je vais commencer par Romain Tessier, qui est professeur à Princeton University. Bruno Després, qui est à distance, qui est professeur à Sorbonne Université. Et puis il y a deux examinateurs, Isabelle Baraf, qui est professeur à Exeter University et qui est à distance également, et puis moi-même. Et puis il y a deux membres qui ont encadré cette thèse, donc Samuel Koch, qui est ingénieur-chercheur ici, et puis Pascal Tremblin, que tous ceux qui travaillent ici connaissent. Donc j'espère que vous entendez bien à distance. Si vous avez un problème, n'hésitez pas peut-être à envoyer un mail ou quelque chose comme ça pour essayer de... Bon, c'est surtout pour les questions aussi. Voilà. Juste pour la partie un peu technique, on vous demandera de sortir à la fin des questions de façon à ce qu'on puisse délibérer ici. Donc les membres du jury resteront sur le GoToMeeting et normalement il n'y aura que ce lien-là qui sera actif. Voilà. Et puis après on reviendra, je pense, ici pour vous donner les suites de la délibération. Voilà, donc on va te laisser la parole pour environ 45 minutes pour nous expliquer tes travaux sur l'étude de la MHD, de la convection en MHD et tous tes travaux liés à cette activité.
Merci. So, hello everyone. Thank you for being here today for my PhD defense. So today, as it's written here, I will present to you my contribution to the study of MHD convection, theoretical framework, final volume methods, and pre-exascale simulation. So convection is at the center of the title and the center of my PhD. So let's start simple by trying to understand what is convection. And let's start even simpler with the simple example of thermal convection. So here we have infrared pictures of a person's hand. As the air is in contact with the person's hand, it's getting heat through conduction. And as we all know, hot air rises and cold air goes down. So we see the air rising under the effect of convection. To describe this simple system, we need several things. We need to be able to describe a fluid, gravity, because gravity is the motor of convection. We need to describe variation in temperature, and we need to describe thermal sources. In this case, thermal sources are conduction and the contact with the hot hand. But convection is not limited to the simple example of thermal convection. For instance, large-scale currents in the ocean are driven by thermohaline convection. It's convection that's driven by gradient of both salinity and composition. And so, driven by temperature and composition, which is salinity in this case, because salty water is heavier than fresh water and therefore goes down. So to describe this system, we need fluid, gravity, temperature, and thermal sources. Thermal sources, in this case, we have solar heating, and we have, again, convection. We now have composition, which is salinity, the concentration in salt, and composition sources, in this case, salt diffusion. So now let's talk about sheared convection. So shear is a vertical gradient of horizontal velocity. For instance, recent observation of the JWST telescope on Jupiter showed that there is a shear profile on the equator of Jupiter that is more intense than what we previously thought. So it's represented here with a big arrow on the surface and a small arrow in the depth of Jupiter. So this is a vertical gradient of horizontal velocity. And so we have reasons to think that shear winds happened in a lot of astrophysical bodies, and therefore they must be interacting with convection. Lastly, magnetized convection in the context of stars such as the sun. These type of stars present a convective zone. So in the outer layer of the star, you have a layer that's made up of convective cells. And since the star is made of a plasma that is ionized, magnetized, it reacts to the magnetic field of the star. So to describe convection in a star, you need many effects. So fluid, gravity, temperature, thermal sources. Composition, in the case of a star, it's the gradient of concentration in heavy elements, such as iron. And composition sources, shear profile, so you can also have shear in a star that's caused by differential rotation. And lastly, magnetic field, of course, and magnetic sources. So in our work, magnetic sources are all non-ideal MHD effects, such as resistivity, Hall effect, or bipolar diffusion. So simulations are at the center of my PhD work. So we start here with all the effects of convection that I just described, all the phenomena that we observe in the universe, and we try to make models, theory, set of PDEs to try to understand better convection. Then from these models, we can derive numerical methods that are specifically adapted to make simulations of these models. And then with these simulations, we can do simulation of convection or further refine our models. And I want to emphasize that during my PhD, simulation were central to improve and understand better our theoretical framework for convection. So this link is really important. Lastly, a really important part of my PhD is high-performance computing, which is the ability to leverage modern computing architectures, so supercomputer. And so when we derive our numerical method, we try to do so with in a way that's adapted to this supercomputer so that we can make even more accurate simulation and improve further our models. So what are the scientific questions I try to answer in my PhD? So we have all these effects, right, that I mentioned before: fluid gravity, temperature, composition, the corresponding sources. And on top of that, we add shear and magnetic field. So if we combine everything, first, how to perform cheap and accurate simulation of convection. Then how to exploit these simulations once they're done. So that's the first part. Then how can we build a theory of convection with all these effects? And lastly, what does this theory tell us? How does shear, magnetic field, and their sources affect convection? To answer this question, I will follow this plan today. Right now we are in introduction. To answer the question of how to perform cheap and accurate simulation of convection, this will be in the second section, so final volume method for MHD convection. Then to see how we did combine all these effects and build a theory, I will explain our theoretical framework for MHD convection. And then it will tell us how the shear and magnetic field affect convection. And lastly, I will explain how we handle I/O in a pre-exascale convective dynamo simulation to see how to exploit these simulations. And then I will conclude. But before going into this, let's first define our equation system. So we need to describe a fluid with gravity in the shear profile. To do so, we use the Euler equation of gas dynamic with gravity source terms that we close with an ideal gas equation of state written here for the pressure. To describe variation in the temperature, we add a temperature dependency here on the lower right of the screen. So a temperature dependency of the pressure. For thermal sources, we add the H term, a heating term, on the right-hand side of the total energy equation. It's on the total energy equation because the total energy contains the internal energy, which describes the temperature. So it's a heating source term. To describe composition, we add a transport equation of a new variable x. X is the mass mixing ratio, and it describes the mixture of the fluid. So for instance, the ratio of water to salt in the ocean. So right now it's purely transported. Then to describe composition sources, well, we add a reaction term on the right-hand side of the composition equation, which can describe diffusion and reactions, chemical reactions. For magnetic field, we couple our system with the Maxwell's equation of magnetism. So we now have the induction equation, which describes the evolution of the magnetic field, and a term of the Lorentz force term on the momentum equation. Lastly, for magnetic sources, we simply add a source term on the right-hand side of the induction equation. That's the full equation system we are working with. Now that the equation system is set, let's see how we simulate this system. First, I will present the final volume method adapted for convection, which is the OSLP solver. So we take a few steps back on the model, and we go back to the Euler equation with no magnetism. So we just evolve density, momentum, and total energy. So classical collocated final volume methods for fluids. They have several pros. So first, they handle shock and discontinuities naturally. They are also fully conservative for all these quantities. But then, if you assume that we are working with a Cartesian mesh and a collocated scheme, we have some issues in the low Mach regime. So the Mach number here is defined as the ratio of the material velocity to the sound speed. And in this case, finite volume methods are typically slow and inaccurate. In particular, if you make a bunch of hypotheses, you can show that the error of the scheme grows as the inverse of the Mach number. So for very low Mach number, you will have a big error in your simulations. Also, the time steps is computed with the sound speed, which is much faster than the material velocity in the low Mach regime, which makes the simulation really slow. You need a lot of time steps. So what does it mean to adapt the finite volume method for convection? So here, let's look at a convection simulation. So we started with a hydrostatic equilibrium, and we sent a small perturbation in this equilibrium. The perturbation goes nonlinear, and we end up with stationary convection wall. So first, convection is typically characterized by a low Mach number, so 10 to the minus 3, 10 to the minus 4. And so we need low Mach accuracy for our method. We need that the error of our scheme must be proportional to the discretization and not the inverse of the Mach number. We also want the time step to only take into account the material velocity. Then, so convection is always a small perturbation around a hydrostatic equilibrium. Hydrostatic equilibrium is equilibrium between pressure gradient and gravity. And so we want the well-balanced property, which means that we solve exactly this hydrostatic equilibrium. This way, we are really precise on studying the perturbations around this hydrostatic equilibrium. Lastly, we want stability. In particular, we're interested in obtaining an entropy inequality, so equivalent of the second principle of thermodynamics, which will imply the stability of the scheme, so positivity of density and pressure. And so the OSLP solver of Powell et al. 2019, Remi et al. 2016 satisfies all these properties. So let's look at it. So OSLP stands for operator splitting Lagrange projection, and it works this way. We separate the equation of gas dynamics into two subsystems. First, the gravito-acoustic system, which describes compressibility, pressure gradient, and gravity. And secondly, the transport system, which describes the linear advection of the conserved quantities. And we solve these systems one after the other. We start from, at each time step, we start from UN, we do the gravito-acoustic step, we obtain the intermediate state U acoustic. And from U acoustic, we perform the transport step to get UN plus 1. So we do one step after the other. And it's during the gravito-acoustic step that we fine-tune the numerical diffusion of the scheme to ensure the low Mach accuracy and the well-balanced property. And the scheme reads as follows. You have the new density, new momentum, new total energy as a function of the old one and the acoustic intermediate step. Now that I've presented this method, let's see how we improved it. So from the operator splitting method, acoustic step, then transport step, we derived a flux splitting method. And the advantage of this flux splitting method is that you can go from UN to UN plus 1 in just one step. So here we have to do two steps, here only one. So it seems as if the splitting disappeared. But so when you implement the method, you don't see the splitting anymore. But to show that the method works, you are still relying on the splitting, and therefore it is still a splitting method. In particular, you can interpret it as computing the pressure fluxes on one hand, computing the advection fluxes on the other end, and doing a convex combination of the results. So since the advection pressure splitting is different from the acoustic transport splitting, let's look a bit more at the advection pressure splitting. So we start with the Euler equation of gas dynamics again, and we do a relaxation of the pressure. So we replace the pressure, the hydro pressure P by pi, and we have now an evolution equation of pi. We also introduce a surrogate specific volume. And then we split the equation into two subsystems. On one hand, the advection subsystem, which is time derivative of a quantity plus divergence of u times that quantity is equal to 0. And on the other end, the pressure system, which contains all that's left. And in this case, we have the pressure gradient and gravity. And we can discretize this system just like we discretized the acoustic system in the previous method to ensure the low Mach accuracy and the well-balanced property. So I recall how we write the old method, the operator splitting method. So again, the new time step depends on the old time step and the acoustic intermediate step. And now this will change. So if we now look at the new method, the thing in red will change. And we just go from acoustic to n. So now we evaluate the fluxes completely at the time step n, instead of at the acoustic intermediate step. So this has several advantages. First, it's easier to implement because it is now a standard finite variable method. If you have an existing code with HLL flux or HLLC flux, you can put this flux function into your code. It will work right away. Therefore, it's easy to combine with a high order algorithm, such as GG, Winnow, Mood, and even adaptive mesh refinement, because these methods are often designed with flux-based method in mind. So here, for instance, we combined it with a Muscle-Hancock solver, second-order Muscle-Hancock high-order strategy, and we observe a nice second-order convergence. Also, the memory footprint is reduced because we don't need to store the intermediate acoustic state anymore. So that's really interesting for high-performance computing application because these applications are typically memory-bound, and so removing the need for storing the acoustic state saves you a lot of memory, and therefore you have better performances. The solver inherits for all the same good properties as the operator splitting methods, and there is a similar CFL condition that is slightly more interesting in the low mass regime. So now that we saw our method for hydrodynamic convection, let's see how we extended it to MHD convection. We now consider the ideal MHD equation with gravity source term. Well, we perform a similar splitting. We have all these effects. On one hand, we look at advection of the quantities. Now there is a magnetic field. So time derivative of a quantity plus divergence of u times that quantity is equal to 0. And then all that's left. So gravity, pressure, and magnetism. Then on this relaxed system, on this splitted system, we do a relaxation that's the same as the one done in Bushy 2010. We also do a smart choice of the relaxation speed to ensure stability and accuracy. By doing so, we get nice MHD simulation on standard test case, such as the Ozakton vortex, the MHD rotor, and the MHD blast. So by using the splitting, this is enough to perform these multi-dimensional test cases, standard MHD test cases. But if we go into the very low plasma beta regime, so the plasma beta number is the ratio of the hydrodynamic pressure to the magnetic energy. So if you go in the low plasma beta number, our simulation still breaks. So let's try to understand why it's difficult to perform these multi-dimensional MHD simulations. So if we want to build the MHD equation, we start with this. So we combine the Euler equation of gas dynamics with the induction equation and the Powell Lorentz force. From this non-conservative system, you can compute several things. You can compute the evolution of entropy. So here we have the entropy equality. And we can also compute that the divergence of B should remain to 0. So if initially the divergence of B is equal to 0, it will remain 0. So second principle of thermodynamics and divergence-free constraint. And we can also show that if our numerical method is entropy satisfied, so if it satisfies this equality, it will be stable. The thing is that we want to do simulation with shocks, so we want to use finite volume. To do that, we need to go into the conservative form of the MHD equation. So to go from the non-conservative form to the conservative form, one needs to add the term that is proportional to the divergence of B into the momentum equation. On the continuous level, this is not an issue at all because divergence of B is equal to 0. From this, we can recompute the entropy equality, and we now have a right-hand side that is proportional to the divergence of B. But in simulation, there is a priori there is no reason why the discretization of the divergence of B should be 0. In particular, it's expected to be of the order of magnitude of the discretization. So if this term is non-zero, it will appear as non-zero here and lead to entropy violating behavior of your solution, and so simulation breakdown because you don't have the stability anymore. So there are several strategies to fix these issues. you can try to reduce the numerical value of the divergence of P. This is constraint transport method and divergent cleaning method. And this improves the stability, but will still break down for low plasma beta test case. So we propose another solution that is inspired by Bushi 2010. So when we go from the non-conservative form to the conservative form, we want to now work with the entropy corrected form of the MHD equation, what we call entropy corrected. It's because we add a source term that is again proportional to the divergence of P to the magnetic field equation that kills this entropy violating term, even on the continuous level. So on the continuous level, divergence of V is still 0, so these systems are equivalent. But on numerics, if now you have divergence error, you are safe because you don't have a entropy violating evolution of the solution anymore. And so, yeah, the entropy, I want to emphasize that the entropy corrected system is still consistent with the original MHD system, which we just now have a corrected entropy inequality. So two strategies for stable MHD simulation. You can do divergence cleaning, constraint transport, and add on top of that pressure fix. So if your pressure becomes negative, do a clip and put your pressure back to a small positive value. This will break locally the energy conservation. But the new idea that we propose is the entropy correction in the low plasma beta regime. So if you detect that you're on the low plasma beta regime, you apply this entropy correction. And this will break locally the magnetic field conservation. I want to note that it's possible to combine constraint transport and divergence cleaning and the entropy correction with any altogether and with any flux function. So it could be HLLD, HLLE, or even the one that we propose, FSLP. So you can combine as you want. So numerical experiments with this new method. So for the MHD, the low plasma beta test case in MHD that breaks down here, we see the yellow value or nonce value in the simulation. If you apply the entropy correction, we get a stable result. Then for the advection of the field loop, so this is a test case where we advect a loop and it should stay similar at its initial condition. By applying the entropy correction, we get rid of these spurious modes appearing. So yeah, that's it for MHD. So conclusion, we improve the flexibility and the memory footprint of the OSLP method by recasting it as a flux splitting method, and that allows this combination with high order algorithm, the straightforward way. And we derive an entropy satisfying multidimensional MHD solver by using modern relaxation and splitting techniques and a entropy correction. So now let's go into our theoretical framework for MHD convection. So my work is based on the work of Trommel et al. 2019, which asks a simple question: under which condition convection starts? So we have a piece of atmosphere at rest at hydrostatic equilibrium, and we send a small perturbation in this atmosphere, and we ask ourselves the question of, is it going to go back to stability, or is it going to grow into nonlinear convection role? So this study is done in the context of thermal compositional hydrodynamics. So we have composition, temperature, and sources of composition and temperature. And my PhD work was to extend this analysis to magnetized and shear flow. To do so, we first need to work a little on the equation system. So here we have the full equation system I presented in the introduction. We need to rewrite two equations. First, the energy equation will become the potential temperature evolution equation. The potential temperature is defined here, and it's simply a variable that is really handy to study convection. On top of that, its evolution equation is a simple linear transport with a heating source term on the right-hand side. Then we have the induction equation that's written in terms of the magnetic field. We rewrite it in terms of the magnetic potential vector that's defined here by uncurling this equation. By doing so, a gauge term appears, and so we need to make a gauge choice to get this purely transport form with a source term. So this gauge choice is required to get the pure transport form, which is required to conduct the analysis. But the criteria, they remain independent. The criteria that we derive from this equation remain independent of this gauge choice because they will be in terms only of the magnetic field and not the magnetic potential vector. So as I said, we will do a linear stability analysis. So we write each quantity as a background quantity and a perturbation. So first, the background quantity, the background state. It's so hydrostatic equilibrium, pressure gradient equals gravity. with a constant gravity, a magnetic field that's constant in the domain, and a vertical gradient of horizontal velocity. For the perturbation, we assume that the perturbation square is negligible, is equal to 0. And we go into the Boussinesq approximation. This means two things. We neglect the pressure perturbation in the equation of state, and we assume that the perturbed velocity field is incompressible. Lastly, we go into Fourier space, which means that our perturbation is a Fourier mode. And so using this Fourier ansatz transforms the set of PDE into a linear system. Here is the linear system. You have this big matrix multiplied with the perturbation vector that's equal to 0. In this matrix, several terms, we have the derivative of the source term. So Rx, Ht, Qa are derivative of the source terms. And we also have the growth rate omega, and in several parts of the matrix. And we see that we are trying to find condition under which the real part of the growth rate is positive, because then this will mean that the perturbation grows exponentially in time. From this matrix, how do we derive the instability criteria? So again, this is the form of the perturbation. We try to find condition on the real part of the growth rate. We have a big matrix times the perturbation vector that's equal to 0, and we don't want the perturbation to be 0. The only solution is that the determinant of the matrix is equal to 0. It happens that the determinant of this matrix is a fourth order polynomial into this growth rate. Therefore, we will apply the Hurwitz criterion, which tells us that if any of these coefficients is negative, the real part there exists a root which has a positive growth rate. So this gives us 4 criteria for the instability. So 4 criteria for 4 coefficients. The first condition, A3, does not correspond to a criterion because it's always positive. Before going further, I want to define some quantities. We have grad T minus grad ad, which is essentially the temperature gradient. And we have grad mu, that is essentially the composition gradient. So A2 negative gives us the adiabatic criterion. It includes the Schwarzschild and Ledoux criteria. And so you essentially sum the temperature gradient and the composition gradient, and you look at the sign of the result, and that will tell you if your atmosphere is stable to convection or not. And so shear and magnetic field appear here, with the magnetic field intensity appearing here and shear here, and they both have a stabilizing contribution that is modulated by geometry. Then second criterion, A1 negative, this is a diabatic branch. So it includes double diffusive convection, so for instance, thermohaline convection and moist convection in the atmosphere. And now you sum the gradients multiplied by sums of the source terms, and look at the sign to see if you are stable or not to convection. Shear and magnetic field appear again, and they again have a stabilizing contribution. Last criterion, A0 negative, is the double diabatic criterion, and so it resembles really closely the previous one, except that the sums of the source terms are replaced by products of the source term. So you do this math, you look at the sign, and this will tell you if your atmosphere is stable or not. So this new instability emerged because we added the magnetic field to the analysis. But what's interesting is that even in this new instability, the magnetic field has a stabilizing contribution. So in a sense, it makes the fluid more unstable because there is a new instability. But within that new instability, it has still a stabilizing contribution. And so this new instability was validated numerically. So I set up a 2D parameter space in which the blue zone corresponds to parameters that are unstable to the new instability and the new instability only. Then I perform a bunch of simulation. Each point corresponds to a simulation, and the color of the point tells you if we saw convection appearing or if it went back to stability. So the green points correspond to unstable convection wall, and the red point corresponds to no convection. So you can see that we really found this new instability and validated its instability zone numerically. Now let's go into the non-linear regime of convection. So our hypothesis for the non-linear regime is that stationary convection is still a small perturbation around a new equilibrium. What I mean by that is that we start with the initial temperature gradient, which is a perturbation in the domain. The growth rate is positive, so we go into the non-linear regime. Convection cells appear, and then in this part of the simulation, temperature is mixed, and therefore we find ourselves here with a different temperature gradient than initially. And around this new temperature gradient, our linear stability analysis is still valid, and gives us a growth rate that's approximately equal to 0 around this new mixed state. So here, if I show my simulation as a function of time, we have the kinetic energies. In the beginning, we are in non-linear regime, then mixing happens. So then we enter a stationary state in which the new growth rate is approximately equal to 0 because the gradients were mixed. So what it means that the analysis is still valid only with updated background profile, so updated temperature gradient, composition gradient, magnetic field, and shear profiles. So they are modified by the mixing. So stationarity means that the real part of the growth rate is approximately equal to 0. And applying the heuristic criterion again, this tells us that all the coefficients are now positive and one is null, and which one is null is determined by the initial conditions. This therefore gives us constraint on the mixed gradient. So if you do a simulation and you have constraint on the composition gradient, on the magnetic field, and on the shear profile, since now we have an equality, we can compute the temperature gradient. We have a constraint. Applying this idea, we can make estimation for the self-generation of shear in our simulation. Because an interesting phenomenon that happens in convection simulation with periodic boundary condition is that if you start your simulation, you will find the beginning cells, convective cells, but then after a while, these cells will be destroyed and go into a purely shear profile. So here there is no convection anymore, just a shear profile. So the velocity goes this way on top and this way on the bottom, and there is no more vertical velocity. So the shear was self-generated. It can also happen with a lower strength. In this box, for instance, we start with nonlinear convection rolls again, and after a while, we can see that the columns have translated, and one roll got bigger than the other. And this is also a manifestation of shear, but on a weaker manner than on the bottom. And so by applying our idea for nonlinear convection, we found that the self-generated shear in these simulations must be proportional to aspect ratio, the aspect ratio of the z height of the box to the x height of the box. So in the square box, this ratio is equal to 1, and therefore it's a high value, and we get strong shear. If we diminish this ratio by going into a elongated box, we have now a ratio of 1/2. We have therefore less shear that's happening. So that's why there is less shear in the top simulation than in the bottom simulation, because of the different aspect ratio. In 3D, we find that shear in the x direction and y direction coexists, and the ratio of their strength, so the ratio of the strength of the x shear to the y shear, is the ratio of the length of the x length to the y length. So in a cubic box, both shear coexist and compete, and no one is really gaining over the other. But if we now elongate the box with x equal 2 here, we have a preferred direction for the shear, and the shear in the x direction overcome the shear in the y direction. And in this simulation, it's essentially 2D, and we see 2D shear appearing. The two walls are translating this way, and one is getting bigger than the other, just like in the 2D simulation there. So it's like a 2D simulation. Moreover, if we compute the kinetic energy, we can see that the y kinetic energy is about 5% of the total kinetic energy of the domain, and the rest is shared between the z and x kinetic energies. Now, we can apply our framework for convective dynamo. So convective dynamo is the self-generation of magnetic field by convection. So you take a plasma, convection happens, so charges are turning around, and this generates magnetic energy. So if we have a plasma in a box with an initial temperature profile and convection starts, this will generate magnetic energy. If we apply our framework, we find that the magnetic energy generated is proportional to the temperature gradient. To test this theory, I made a bunch of linear simulations with varying temperature profile. And then I superposed here the value that we obtain in the simulations in blue and the value from the theoretical framework with the red line. I need to emphasize that this red line is obtained by fine-tuning a geometrical factor. So we need to fine-tune the value. And this value was fine-tuned to 0.34 for a box of size 1. That's a reasonable scale. And so we have a good agreement of both quantities. I think that we understand well what's happening there in these simulations. So that's it for our theoretical framework for MHD convection. So quick conclusion, we included the shear and the magnetic field to the linear stability analysis for convection, and we were able to measure their stabilizing effects. We discovered a new instability, that we call double diabatic, and verified its existence numerically. And lastly, we performed nonlinear simulations of the self-generation of shear and magnetic field, and were able to link these simulation results to our theory. Now let's go into the last part. So how did we handle I/O in a pre-exascale convective dynamo simulation? First, I will start with a really quick introduction to high-performance computing, exascale, and the I/O bottleneck. So here I show the evolution of the computational capacity of the fastest supercomputer in the last 30 years. And as the y-axis is in log scale, we can see that this growth is exponential. And in particular, we recently reached the exascale. The exascale means that we have supercomputers that are able to perform 10 to the power 18 floating point operation per second. This was achieved by the Frontier supercomputer in the US, which is essentially, long story short, a lot of GPUs put together with a capacity to communicate with each other. The GPUs of Frontier are the AMD MI250X, but another recent brand of GPU that's worth mentioning are the NVIDIA 8100 GPUs. As the computational capacity grew exponentially, the I/O bandwidth of the supercomputer, so the velocity at which they are able to write on this, did not grow as fast. In particular, here I showed the ratio of this I/O bandwidth to the capacity of the supercomputer, this ratio in the last 20 years. And you can see that it's decreasing sort of exponentially. So there is an increasing gap between compute performances and I/O performances in the large-scale systems. And so this ratio was divided by 10 over the last 10 years. So when the Adastra supercomputer in Montpellier was built, a call was made for grand challenges, and so me and the team answered to perform a large-scale convective dynamo simulation on Adastra, but with using modern HPC I/O tools to exploit our simulation and deal with this I/O bottleneck. So let's see what was the strategy for our simulation. First, the scaling of the problem. So we have convection in a cube, and we have 4,096 cells in each direction, and 9 variables per cells. All this data is shared between 1,024 GPUs, and during 60 hours of real time. And so a full output of the simulation weighs 5 terabytes. If you want to write your solution on disk, you need 5 terabytes. So the question is, how do you look at so much data? That's the modern problem of exascale computing that we're trying to tackle here at Maison. So there is too much data to process full outputs. You cannot save hundreds of outputs and look at them afterwards because you don't have that much storage. So we need to perform reduction during the simulation, so averages, slice, and reduction along axis. And to do so, we use the parallel data interface that allows to couple your high-performance computing code with various libraries. And in our case, we couple it with the HDF5 library. We also did in situ data analysis of the solution using Deisa. So Deisa is DAS-enabled in situ analysis. That's the PhD work of Amal Gerouji in 2023 here at Maison Simulation. And this allows to run DAS code, so data analysis code, on your simulation data, but on separate computational resources than the one used by your simulation. And we believe that this type of tool will become essential in the exascale era. So our strategy. Here I have the kinetic energy and magnetic energy in our Convection simulation as a function of time. And we can see that the nonlinear phase takes quite a long physical time. And we are not interested in the linear phase, we want to study the nonlinear regime. So to bypass this long linear phase, we did several upscaling of the solution. So we start at a low resolution, 256 cube, and we progressively upscale the resolution by 2. So, and this corresponds to the vertical blue lines here. So the question is when to do the upscaling, and the answer is when the flow has converged. And how to check that the flow has converged? This is by looking at the kinetic power spectrum of the simulation. The issue is that the kinetic power spectrum simulation that we did is only on the slice of the simulation. Therefore, it does not scale to the full machine. You only need a few GPUs, a few computational resources to compute this. So if you try to compute this at a very high frequency, you are not efficiently using your whole GPUs. So instead, we use the Deisa library to compute it during the simulation on separate computational resources. And here, I'm superposing the kinetic power spectrum of computed from a full output versus the kinetic power spectrum computed by Deisa during the simulation. So we believe that this is a stepping stone for self-piloted simulation. In particular, we would like to do something like Deisa detecting that the flow has converged and sending a signal to the simulation to upscale itself instead of doing the upscaling ourselves. So this signal sending is a project that's currently investigated at Maison Simulation. Here I will show a video. So video of the density perturbation, a vertical slice of the density perturbation of our simulation. So orange is heavy and yellow is light. So we can see in the beginning we have a heavy plume that goes down and also light plumes that goes up. It also seems that material is coming through the screen, and that's the case because this is a slice of a 3D simulation. So there is plumes that are going through the screen. So this is non-conservative. Here we have a descending plume of heavy fluid again. So yeah, that's it for the last case simulation. In conclusion for this part, we ran a grand challenge simulation of convective dynamo on the Adastra supercomputer, and we leveraged the PDI and Deisa libraries to be able to build our simulation. Now, let's conclude. So I asked a few questions in the introduction, and we tried to answer them. How to perform cheap and accurate simulation of convection. We try to improve on this matter by improving the flexibility and memory footprint of the OSLP solver and extending it to MHD. Then how can we build a theory of convection with all these effects? This was done by adding shear and magnetic potential vector evolution equation to the linear stability analysis. And for the nonlinear regime, we studied this regime by assuming that the nonlinear regime of convection is marginal stability. Third question, how does shear, magnetic field, and their sources affect convection? We found that they both have a stabilizing effect on existing criteria, but they also generate a new instability, and their stabilizing effect is heavily modulated by geometry. In the nonlinear regime, they can both self-generate to saturate the criteria. Lastly, how to exploit this simulation. So in the case of large-scale simulation, we need to combine HPC simulation codes with a modern IO library, such as PDI and Deisa, to perform in situ analysis of the solution. Some other takeaways. So throughout my PhD, the splitting of transport and acoustic/sources effect was a very powerful tool. So we used it to derive the theory of convection by using the potential temperature equation and the induction equation, this purely transported form were handy, but we also use them to derive our numerical method that rely on splittings. So seeing that splitting is a really strong idea for both numerics and physics. Regarding convection, it seems that adding effects to the analysis of convections not only modify existing criteria, but can also derive new criteria. So we think that our framework is really handy to take into account new criteria and see the full implications of adding, to add new physics and see the full implications of these new physics. And lastly, most important, I would say, is that simulation should not be opposed to theory. Rather, it can help developing the ladder. I hope that my PhD convinced you of that. For the perspectives, so how to do even better, how to perform even cheaper and more accurate simulation of convection. So we first need to more fine-tuning of the Loma correction of our method, because it's not perfect. It has some issues that I did not mention in this presentation. We also need to derive an implicit-explicit strategy for the discretization that will circumvent the Loma gradient time step issue. We need to adapt the MHD solver to high order and complex geometries. In particular, we need to look at how to discretize the entropic correction software. How can we make the analysis of convection even more complete? We need to study the shear and magnetic field interaction, and we need to add, because that's something that we've not done during my PhD, we also need to add kinematic viscosity to the analysis. Then how can we leverage the analysis that I've done? So we need to develop a missing length theory from our framework. This will allow us to use it in a 1D atmospheric control and apply it to real astrophysical bodies. And the one we have in mind are magnetic chemically peculiar stars. We also need to study the emergence of shear-induced convective staircase. This was the internship of Mathieu Lecomte. And lastly, how can we further improve our large-scale simulation I/O pipeline? We need to develop a feedback mechanism from Deisa to the simulation code and conduct these self-piloted large-scale convective simulations. Thanks for your attention.